All right, everybody. These notes are not like an all-inclusive thing. They're more so used to hopefully fill in some gaps if you tried the homework the other day. So, we're taking a look at inverses once again. We're going to talk about them in a little bit more depth. We have defined a relation to be a mapping of input values with output values. An inverse relation maps output values back to their original input values. So when I say output, we're talking y. When I say input, we're talking x. So for letter A here, it says the original relation is 0, 0, 1, 1, 2, 4, 3, 9. So then the inverse relation here is going to be 0, 0. The first one doesn't change. 1, 1 also doesn't change. But now we go 4, 2, and then 9, 3. Okay? So let's graph the relation and the inverse and the line y equals x here. So the original relation, we'll make that this orange color, so 0, 0, 1, 1, and then we have 2, 1, 2, 3, 4. Then we have 3, 1, 2, 3, 4, 5, 6, 7, 8. Looks like 9 does not fit on this graph. Not sure what I was thinking here when I made this graph up. Okay? So this relation would look something like this. It's also telling us to graph the line y equals x, so it'll go through right here, just like that. And then graphing the inverse relation, we're at 0, 0, 1, 1, 4, 2, 1, 2, 3, 4, up 2, and then 9, up 3, should put us right here. And so if we graph this one, should look like this. I'll draw it a little better. Like that. Okay? So, what did you get the ordered pairs for the inverse relation to be? Okay, so the ordered pairs here for the inverse relation, we can basically just say that the y's, or the y's became x's, and x's became y's, right? Just like yesterday we talked about how the x's and y's swapped. So what conclusion can we make about the domain and range of an inverse relation compared to the original relation? If we take a look at this, right, if all of the y's became x's, that means the range, which is all of the y's, becomes the domain. And if all the x's become y's, the domain becomes the range. All right, so that's what we can say about the domain and range. They literally are flipping. Just like the x's and y's flip, the domain and range also flip. So how does the original graph and the inverse graph relate to each other? Try to see a visual geometric connection. Well, we talked about this yesterday, right? The inverse is a reflection over y equals x. All right? So, what if instead of a set of ordered pairs, you were given an original equation? How would you find its inverse? Think about what we just did. Well, yesterday I told you, right? You're just going to switch x and y and then resolve. So, we say x is equal to 2y minus 4. And then if we want to find this inverse, we add 4 to both sides. That gives us x plus 4 is equal to 2y. And then we just divide everything by 2. So x plus 4 over 2 is equal to y. And that would be the inverse equation. It says graph the relation, its inverse, and the line y equals x in the same coordinate plane using your graphing calculator. And then sketch what you see or copy a picture of it. What do you notice about the graphs? In comparison to y equals x. So go ahead and try that out, guys. And then take a look at the key and make sure that your graph, either in Desmos or on your graphing calculator, it looks similar or it looks the same as the key. All right, continuing on. We can prove that two functions are inverses of each other using compositions of functions. We also talked about this the other day. The notion for inverse of f is f inverse, all right? and I tried to stress this yesterday, but we don't want to confuse this with negative exponents. It's simply the notation that is used for inverses. All right, it's not the reciprocal function. So if f and f inverse are inverses of each other, then when we plug in f inverse into f, we should get out an x. And when we plug f into the inverse of f, you should also get out x. That was just like saying if we had f of g of x, we should have got out x. And then if you have g of f of x, you should also get out x. And that's how we verify inverses. So if you missed that from yesterday, right, it says prove f and f inverse are inverses of each other. Let's take a look at this then. So it says plug f inverse into f. So that's literally saying we're going to have 2 multiplied by 1/2 x plus 2. Right? We're taking this equation and we're plugging it into x. So that's 2 multiplied by the equation and then minus 4. Some simplifying, we distribute the 2. That gives us x, plus 4 minus 4, which just leaves us with x. If we do the reverse operation where we plug in 2x minus 4 in for x to this equation, we're going to get 1/2 multiplied by 2x minus 4, and then that's plus 2. Distribute the 1/2 to get x minus 2 plus 2, and then negative 2 and positive 2 cancel to just give us x. Number 4 says find the inverse equation of y equals x cubed. Right? So if we're doing that, we just swap the x and the y. So we say x is equal to y cubed. And then you cube root both sides. So that gives you the cube root of x is equal to y. It says graph y and its inverse on the same coordinate plane using a graphing calculator and sketch what you see. Is the inverse a function? So I want you on a graphing calculator or in Desmos, either one is great. I use Desmos in the key. Go ahead and graph both the inverse function and the original function and verify that they are in fact inverses of each other. Number 5. So if we want to know if our original relation is a function, we can use the vertical line test on its graph. So, can you tell by looking at the graph of an original function if its inverse is a function? All right. Yes, right? We talked about this yesterday. It's the horizontal line test. All right, number 6. Number 6 says determine whether the inverse of f is a function and then find the inverse of f of x. Find the inverse of that function. You should explain how you knew if the inverse was a function or not. So let's first find the inverse of this function. In order to do that, we're just going to swap the x and the y. Okay, so we're going to say x is equal to 2/3 f inverse of x, and then that's getting cubed minus 4. So we would add 4 to start. So that's x plus 4 is equal to 2/3 f inverse of x cubed. Then you multiply by 3/2 on both sides to get off that 2/3. So that's going to give you 3/2 multiplied by x plus 4 is equal to f inverse of x still cubed. And then the last thing you need to do here is cube root both sides. So you cube root the left side, cube root the right side. So that's the cube root of 3/2 multiplied by x plus 4 is equal to f inverse of x. All right. So the next part says determine whether the inverse of f is a function. Right? So how can we determine if the inverse of x is a function just by looking at the equation? The biggest way to tell here is to talk about what is the function that's getting created. All right? This is x cubed to the 2/3 minus 4. So then a cubic function actually, we don't necessarily know if a cubic function does this. right? Because then the inverse would not be a function. So in this case, guys, I think you would need to draw the graph of 2/3 x cubed minus 4. Determine whether the inverse of f is a function and then find the inverse of that function. You should explain to me how you knew if the inverse was a function or not. Yeah, this is a graph question. Okay, so graph in graph calc. And see if it passes the horizontal line test. If it does, inverse is a function. If it does not, then it's not a function. All right, next, it says consider the function f of x equals x squared. First, we want to graph it. This is an easy graph, hopefully, because we've done quadratics. Goes through 0, 0, to the right 1, up 1, to the right 2, up 4, and then to the right 3, up 9, which would just go off. And then you graph the reflection, right? So this is the graph, whoops. This is the graph of y equals x squared. It says, is the inverse a function? How do we know? Draw a horizontal line. Does not pass the horizontal line test. And you can just put horizontal HLT line test. That's how we know the inverse does not pass horizontal line test, so not a function. Okay, so not passing the horizontal line test is enough explanation. It says next, now graph f of x for x squared only for x greater than or equal to 0. So you actually, if you were paying attention to it, saw this on the homework yesterday and we're probably like, what even is that? This is telling us restrict the domain to only the x's that are greater than or equal to 0. So 0, 0 is 1 point, 1, 1 would be another point, 2, 4 would be another point, and then 3, 9 would be even another point right here. We wouldn't graph anything to the left of 0 because it's telling us that the domain is all the x's greater than or equal to 0. So this is the only portion of the graph that we have right here. Okay? Next, it's saying, is the inverse a function? How do we know? Well, in this case, because we only graphed the right side of this function, yes, the inverse is a function. It passes the horizontal line test, HLT. It says find the inverse equation for part C and graph it on the coordinate plane. You just used in a new color. Before we even find this inverse, we need to first either restrict its domain or its range based off of the domain restriction in the beginning. So in the beginning here, we have all of the x's have to be greater than or equal to 0. So that means for our inverse function, the y's have to be greater than or equal to 0. And this is because the domain becomes the range, right? So originally x was greater than or equal to 0. If that's going to become the range, that's telling us y is greater than or equal to 0. So then we just swap x and y. So we have y, or x is equal to y squared. You square root both sides. You get the square root of x equals y. In this case, we don't need to put plus or minus because it only wants the y's that are greater than or equal to 0, which is only the positive square root of x. The negative square root of x would be the y's that are less than or equal to 0. All right, so that's why we don't include it. So if we're graphing this, it's going to be 0, 0. When you plug in 1 into this equation, it gives you positive 1. When you plug in 4 into this equation, it gives you out positive 2. And then 3 would give you out 5, 6, 7, 8, so it doesn't quite go that far to 9. So we're just good right there. Okay? So, explain/draw what would have been different if you would have found the inverse of the entire parabola from part A, right? So the difference is, if we would have found the entire parabola, then we would have had to say, when we wrote that square root of x is equal to y, we had to put plus or minus, and then you would draw the top half, and you would draw the bottom half, right? So this bottom section doesn't exist because of the domain restriction from letter C, all right? So that's why some of those questions yesterday said x is greater than or equal to 0 or things like that, all right? Technically on this as well, this is y is greater than or equal to 0. So then the other part of this equation is that the x's are greater than or equal to 0 as well, because domain and range literally flip their roles. So knowing that, go back through and look at the homework from the other day and make sure that those domain restrictions are making sense. And if they're not, we should definitely talk about them. All right. Hope you guys have a great day. And I hope this helped clear up some inverse stuff and also just give you an idea of why those had x is greater than or equal to in some cases. But yeah, I will see y'all soon.